If we click on the context, so this talks about what's really the application domain we are trying to solve. So we have three constants here, n, f, and v, and n specifies the size of the array, and f will be used is a variable that will be used to formalize an array by a function, and v specifies the elements that we are trying to search within f. So let's see, because n, f, and v only declaring n, f, and v as constants would not be sufficiently enough. So what we need is to declare axioms to say what their properties are. So first of all, we'd say f is a function from a domain into a range, and a domain is actually an interval from 1 up to n. So this is really the set of indices that we can refer to within the array f. So the indices start from 1 and end with n. So here we can see that n really represents the size of the array, because the array size, the array index starts with 1. And here we're saying that the array stores natural numbers, because natural numbers is in the range. And the second axiom that we're trying to declare here is the sorting property. So we are saying that for all the indices I and j, where I is within the range of 1 up to n, and j is also within the range of 1 up to n, if it is the case that I is smaller than or equal to j, then it must be the case that the elements contained at index I within array f must be smaller than or equal to the elements contained in j. So this is saying the array f is sorted in the non-descending order. And the third axiom guarantees that v that we are searching for must exist in array f, because we're saying because the range of f is natural number, and if we say that v is in the range of f, we're saying v must be there. It must be one of the natural numbers that f stores. And here we actually have a theorem here to prove. So this is to say n is larger than or equal to 1, which means f in the smallest case, for f, f will be its index set will be from 1 to 1, which means it has just one element, but it's guaranteed that f cannot be empty, and this can be discharged automatically from Rodin. It's mainly because if v that we are trying to search is guaranteed to be in the array f, then of course f must be non-empty. So this theorem is trivially to be proved, and it has been discharged by Rodin. Let's now go to the machines. So basically we have three machines. We have the abstract machine M0, and we have two subsequent refinements. The first refinement results in a machine called M1, and the second refinement results in a machine called M2. Let's first look at M0. M0 is rather short, but the critical variable to declare is R, and R here is the pivot position within the array f that we are trying to search for. Remember that it is assumed that f is sorted, so every time we're supposed to choose a pivot, and we just will pivot index, and we will compare the elements stored at the pivot R with the target elements v. And because the array is sorted, so once we and we have to keep reassigning the value of R until that we actually get something, some index where its contained element is equal to v. That's basically the searching process. But in the abstract level, we don't actually specify exactly how the whole searching process is going to proceed. Instead, we say initially R is assigned to be some natural number, and to make the progress, so this progress here abstracts away the searching process. So it represents that. So every time we are just going to reassign some value to R non-deterministically. So the colon member symbol represents non-deterministic assignments. So here we say we will keep reassigning the value to R until to the point that f of R is equal to V. But how we actually get to the point that f of R is equal to V, as far as the abstract level is concerned, we don't care. Okay, so now in the subsequent refinement level, we actually be more specific about how this progress event is going to be achieved. And as you can see, at the abstract level, progress is declared to be anticipated. That means we anticipate to refine this progress later. And we have to make sure that this progress event cannot simply just go on and on and on without terminating, because we want to make sure no matter how large the array F is, the searching process cannot go on and on and on. It must terminate eventually and give us the result. Okay, let's go to the first refinements. So basically, in each refinements, in each of the two refinements, we are just being a little bit more specific about how we choose the pivot value and how we, based on the pivot value of the index, how we actually continue with the searching process until we find the element V. Let's go to the first refinements. And here, except for the R that has been already declared in the previous abstract machine, we declared two new variables, P and Q. You can think of P and Q are the lower bounds and upper bounds for us to narrow down the search space. So now we are trying to, so as you can see, we now actually refines the progress events by two events in this level. So as you can see, the event increments refines progress, and the decrements events refines progress. And both of them are declared to be convergence, meaning that they will eventually terminate. You cannot simply just call increment, increment, increment for infinite number of times, and similarly, you cannot call decrements for an infinite number of times. So now, let's have a look at how this refinements level is trying to specify. So we have the lower bounds P and upper bounds Q, and they must be within the range of 1 up to n. And remember, n is the size of the array, so P and Q should always be maintained as a valid index for the array. And R, we have a stronger constraint to say R, which is a pivot value, must be in the range of P up to Q. And we are trying to maintain the invariance that P up to Q is maintained as the search space, and we want to make sure that within this range, V must be there. So this square brackets notation is called a relational image. So P up to Q is a set of indices, and F is a function, and a function is also a relation. So applying this relational image expression to interval set, what we would get would be a set of natural numbers, which are the contents that are contained in this interval P up to Q. If you're not sure about how to apply this relational image operator, you're supposed to refer back to the slides for its formal definition. Okay, and here we have a variance section, which means because we declare the increments and decrements events, which both refine the abstract progress events as convergence. As soon as you declare the events as convergence, you have to specify a condition such that the condition is a natural number expression, and you will eventually, every time you execute the convergent events, the variance expression will decrease its value by at least 1, and eventually this variant expression will reach to 0, and upon reaching to 0 value, the convergent event will start to be executed anymore, which means it guarantees termination. So let's see. So now in the initialization, in addition to assigning some value to R, we also initialize the values of P and Q to be 1 and n. So initially the search base covers the whole array. And the final event remains the same because as soon as we have the condition that f of r, where r is the pivot value, where f of r is equal to v, then we are done with the whole searching process. And now, how we actually make progress for the searching process will rely on the increments and decrement events. So basically, let's consider a diagram here. So this is the case of increments. So this is the case where the current value of the pivots actually contains a value that's actually smaller than the target value v. In which case, we will try to increase the current lower bound by we'll try to reassign the current lower bound, which is p, by the value of r plus 1. And how we actually maintain the invariance that it is guaranteed that v is still in the new interval of p prime and q. We will actually show you how to prove this later in the later video. But this is the conceptual idea of how the progress can be made when it is the case that the current value of pivot value r contains the element that's smaller than v. On the other hand, for the other case where when the current pivot value contains the elements that's larger than the target value v that we're looking for, in which case we want to reassign the value of q to a value that's strictly smaller than r. And in this case, in the first refinement, we'll choose that to be r minus 1. And how we actually maintain the invariance that in the new interval p and q prime that the target element v is still there. We will actually prove in the later video how this is the case. So let's go back to the Rodin, and this is exactly what we just said for the diagram. So in this refinement level, we are trying to reassign the value of the lower bounds p and the upper bounds q depending upon how the pivot value elements is compared to the target value v. As you can see here, we are simply just do r plus 1 and r minus 1. But this may not be sufficiently efficient enough. So what we will do in the next refinement is to try to reassign the value of p to reassign the value of r more efficiently. And that's why the whole searching algorithm will be more qualified as the binary search in the next refinement. Let's just go on and see how that can be achieved. In the second refinement, we still have the pivot variable r, and we have the lower bounds p and upper bounds q. And now, as you can see, the way we update p and q are that initially p is assigned to be 1, q is assigned to be n, which means the whole we start with the search. We start with the searching area that covers the whole array. And for the increments case, we actually assign p to be r plus 1. And in the decrement case, we assign q to be r minus 1. These are exactly the same as the previous refinement level M1. The only difference here is how we reassign the value for r. In the previous refinements, let's just remind ourselves, we actually reassign the value of r by some non-deterministic assignments, which means as long as r is within this range, then that's okay. And as you can see here for the decrements case, it's also the case. As long as r is within the range of p up to r minus 1, then we don't care which value you choose. As we mentioned, this may not be sufficiently efficient enough. What we want to do is to have a more sophisticated calculation. So in this case, we actually want to get the middle point between the lower bounds and the upper bounds. So as you can see, we are trying to do some well-known division here. So we are trying to simply just get a middle point between r and q here, and also here we are trying to get a middle point between p and r minus 1. That's basically the fundamental difference between the two refinements. And in later videos, we actually try to prove the consistency between the refinement number 2 and refinement number 1 is to make sure the way that you assign this division expression here, for example, let's say for the increment events, the way you reassign this value to R is consistent with the way you do the non-deterministic assignments over here. That's actually how you prove the consistency between the two refinements. And we'll show you in the later videos how you actually achieve this. Okay, so now we have just finished a very brief overview of what you have got so far. For the binary search problem, you have one context, you have one abstract machine, and you have two refinement steps. And we have many proof obligations undischarged. And in later videos, we'll try to help you on discharging all the proof obligations.